Radio frequency fundamentals. In order to place wireless LAN equipment in their optimal locations and to troubleshoot wireless LAN connectivity issues, it's really important to know how a radio wave behaves when it propagates or moves away from an antenna. And that's exactly what we're going to learn about in this video. So we're going to start things off by learning about the terms and concepts of what happens to a radio wave when it's transmitted from an antenna and meets an obstacle in its path. And there's different types of behavior that happens to radio waves depending on the types of obstacles that it encounters as it's being transmitted from the antenna to the radio receiver. And we'll also learn about radio frequency antenna concepts, and we'll finish off by learning about the units of measurements used in radio frequency mathematics. So get your radio and tune it to CBT Nuggets because we are going to get started. So first off, we're going to learn about the different behaviors of radio frequencies, and to do that, we're going to bring up another whiteboard. Now, if you remember from our previous video, RF stands for radio frequency, and a radio wave is an electromagnetic wave that is propagated or transmitted by an antenna. And radio waves have different frequencies. So when you're using a radio to tune into a station, you're tuning into a very specific frequency to listen to the music that's broadcasted at a specific frequency. And frequency means the number of times a radio wave will oscillate up and down per second. So for example, if you were to listen to an AM frequency of 680, that means that that radio wave goes up and down 680,000 cycles per second. In contrast, FM works at a higher frequency level. So for example, if you were to listen to a broadcast on an FM frequency of 101.5, what's actually happening in the background is that the radio wave is being transmitted at 101,500,000 cycles per second. And one of the main benefits for broadcasting radio broadcasts using FM, which stands for frequency modulation, is that FM is pretty much immune to static because the actual FM frequency wave changes very, very, very little. And as a result, you've got a nice, strong, clear, clean signal. Now, a radio wave signal can be either increased or decreased, and the terms to represent these are gain and loss. Gain is used to increase the radio frequency or radio wave signal's amplitude, and amplitude is the height of a radio wave signal. So, for example, we can amplify the signal to increase the signal strength. And we can increase the gain of a radio frequency signal strength by using a radio frequency amplifier, or we can simply use a high gain antenna to also focus the beam width of the signal to increase its signal amplitude. So we can amplify the signal by either using an external power source or by using a high gain antenna. In contrast, loss is the term that's used to describe a decrease in radio frequency signal strength. And loss can occur while the signal is being transmitted through the cable and while it's being transmitted through the air. For example, impedance mismatches in the cables and connectors can cause the power to actually be pushed back or reflected back to the transmitter. We'll learn more about impedance in a few more minutes here. Another situation that can cause loss is if there's objects that are directly in the radio wave's path. So, for example, when the radio wave is being transmitted from the transmitter to the receiver, if we have objects between those 2 points, that can cause the radio wave transmission to either be absorbed or reflected or even be destroyed. So if a radio frequency signal is experiencing loss due to objects in its path, we can either remove those objects, which is going to be a little difficult if that object is a skyscraper or a mountain, or we can increase its transmission power by increasing the gain of the radio frequency signal. Now, a radio wave will exhibit a very specific type of behavior when it encounters an object in its propagation path. And as you can probably imagine, there are terms that define what happens when a radio wave meets these objects. And the first term is called reflection. Let's bring up a whiteboard and learn about reflection. Now, reflection is pretty straightforward. This term is used to describe what happens to an incoming radio frequency when it bounces off a very large surface. So, for example, the surface of the Earth could reflect a radio frequency. A building could reflect a radio frequency. Walls can reflect a radio frequency. So the radio frequency comes down, hits that surface, and boom, gets reflected right off. Now, if a radio frequency bounces or reflects off many surfaces during the course of its transmission, this is referred to as multipath. And multipath can cause some problems, as you might imagine. So multipath can cause problems with the wireless LAN, such as degrading or even canceling out the signal altogether, or simply causing holes or gaps in a radio frequency coverage area. Now, another behavior is called refraction. Let's bring up another whiteboard and learn about this. Now, refraction can occur when a radio wave passes through a medium of different density. So, for example, when a radio wave is passing from warm air to cold air, that cold air is a different density. And as a result of passing through that cold air, the radio wave can be bent as it's passing through this cold air. And the bending of that radio wave actually changes the direction of the radio wave, as we see here. So we've got the incoming signal, it hits the cold air, and then it is bent and then changes direction of that radio wave. And this can be a real problem when a radio wave has to travel over very, very long distances and has to go through different atmospheric changes, such as going from warmer air to colder air. Now, a real classic example of refraction can be found on Pink Floyd's album cover for their album The Dark Side of the Moon. I just happen to have a graphic of that album right here. So in this example, this album cover illustrates a light wave being bent as it passes through this glass prism, and as a result it changes direction and it comes out in this direction on the other side of the glass prism. So classic example of refraction for your Pink Floyd fans there. Now, in addition to a radio wave bending as it passes through a medium, a radio wave will also bend as it passes around an object as well. Let's bring up another whiteboard and learn about this. When a radio wave passes or turns or bends around an object, this is referred to as diffraction. So again, just to make sure that we have these terms clear here, refraction occurs when a radio wave is being bent through a medium. In contrast, diffraction occurs when a radio wave turns or is bending around an obstacle. So in this example, we have an antenna emitting radio waves, and the radio waves hit a rooftop, and the radio waves are bending or turning around the rooftop and are changing direction as a result of bending around that obstacle. Now, so far we've been learning about what happens to a radio wave, or how does a radio wave behave when it hits relatively large objects in relationship to the radio wave. Well, what happens to the radio wave when it hits smaller types of objects? Well, let's bring up another whiteboard and learn about that. If a radio wave were to strike objects with dimensions that are small compared to the wavelength of the signal, the radio wave scatters. So in this example, we have a radio wave that is hitting some jagged edges of a rock. And in that situation, the radio wave scatters out, and what happens here is that the radio wave is reflected in many directions simultaneously. And the scattering of a radio wave can occur when the radio wave strikes uneven or jagged surfaces, such as rocks or street signs or lampposts or sand, or even particles in the air. So, for example, if a radio wave were to go through a dust storm with lots of particles in the air, the radio wave would scatter out and be reflected into many directions. And also, there's instances when a radio wave strikes an object, it might be absorbed into the object that it's striking. So if we bring up another whiteboard here, we can see that this incoming radio wave hits this type of material where the material doesn't allow the radio wave to pass through it, reflect off it, or bend around it. It just simply absorbs the actual radio wave into the material of the object. And as a result, this type of behavior is simply referred to as absorption. For example, military aircraft that uses stealth technology has a coating that absorbs radar signals. Now, so far we've learned about radio wave behavior as it encounters obstacles along its path to a receiver. However, there can be obstacles and problems with the RF signal even before it's sent. Let's bring up another whiteboard and learn more about this. A problem named voltage standing wave ratio, or VSWR for short, can occur as the radio frequency signal is being sent from the transmitter up to the antenna. And the problem is if there's a mismatched impedance between the devices in a radio frequency system, this can cause the power to be reflected back toward the transmitter. Okay, well, what does that actually mean? Well, let me bring up another whiteboard which illustrates the problem of VSWR. In this illustration, I have two hoses which are connected together. So I have a hose here with a large diameter, and over here I have a hose with a narrower or a small diameter, which in turn is connected to a water faucet. So in this particular example, as water flows through the water faucet into the hose with the larger diameter and then meets up with this hose with the narrow diameter, there's going to be some back pressure placed on this connection point of these two hoses. And in terms of what we're talking about, this back pressure is referred to as impedance. So as water flows through the hose with the larger diameter and then meets up with the hose with the narrow diameter, the flow of water is impeded, or it's slowed down as it tries to eke its way through this narrow connection here. So this is referred to as a higher impedance connection, whereas the hose with the large diameter has lower impedance. We have a larger diameter which allows for a greater amount of water to flow through that hose. Now let's relate this back to what we're learning about here. Impedance is electrical resistance, and electrical resistance is measured in ohms, and ohms is abbreviated as OHMS. And you may have heard about ohms when you purchase speakers for your home audio system. So for example, if you're upgrading your home audio system to create a surround sound system, you want to check to ensure that all the speakers in your surround sound system have the same ohm level. And most speakers these days have a rating of 8 ohms or have an impedance of 8 ohms. And the higher the number of the ohms are, that means that there's going to be a greater amount of resistance, and overall that will mean that there will be less power that can be delivered by an amplifier. Now, one of the things we have to watch out for is when we're configuring a wireless access point with an external antenna which is connected to the wireless access point through a series of cables and connectors, we have to ensure that each of the components between the wireless access point and the antenna have the same impedance level. So what we have to keep in mind is when we're creating a wireless access point with the external antenna is that if the impedances of the ends of the connection don't match, then what's going to happen is the maximum amount of the transmitted power will not be received by the antenna, and because of the higher impedance, you'll find that some of the signal will actually start to flow backwards. So we've got this bottleneck right here. So we've got this forward motion of energy, this signal, this radio frequency signal is chugging along, and then bang, it hits this almost like a brick wall here. It's trying to squeeze all this forward motion through this higher impedance connection, and as a result, you're not going to be able to get as much signal strength through that connection, and you're going to have a buildup of signal strength right here, and some of that signal strength will actually return back to the source, and this is referred to as return loss. This returning back of the signal strength is a return loss. So a few things can happen when we have this signal strength being reflected back to the transmitter. Number one, the signal level on the line varies quite a bit, so instead of having a nice steady strong signal, it's going to vary. Also, what's going to happen is that the amplitude of the signal is also going to decrease as well. So we've got this lower impedance connection, and then bang, we hit this higher impedance connection, and that's going to provide resistance, and as a result, that's going to decrease the amplitude of the transmitted radio frequency signal. Now, another thing you have to watch out for is that some transmitters are not protected against power being returned back to the transmitter, and this reflected power can actually burn out the electronics of some devices. So to avoid these problems associated with voltage standing wave ratio, or VSWR, which again is mismatched impedance, is simply to use cables and connectors of the same impedance, which again is measured in ohms. So you want to make sure that all of the cables and connectors are rated at the same ohm level. And also make sure that there's a nice, tight, strong connection between all of the cables and connectors as well. Now, VSWR itself is actually expressed as a ratio. So, for example, we'd have a ratio of impedance mismatch against a perfect impedance match. So we might have an impedance mismatch of 1.2 to a perfect match of 1. So we've got a ratio of 1.2 to 1. So the closer we can get this first number to 1, the better impedance match we're going to have, and as a result our system will behave better. So the ideal situation is to have VSRW of 1 to 1, or a ratio of 1 to 1. And with a ratio of 1 to 1, that would denote a perfect impedance match, and no voltage standing wave would be present in that signal path when we have a ratio of 1 to 1. So again, this 1-to-1 ratio can be achieved by ensuring that every device from the transmitter to the antenna have the same impedance level. So for example, you wouldn't want to use a 75 ohm cable with a 50 ohm device. Now, thankfully, most of the wireless LAN devices have an impedance level of 50 ohms, but make sure you double check everything before you purchase and put your wireless access point together with its cables, connectors, and antenna. Now, speaking of antennas, there's a few key things we need to know about antennas. Now, we've got an entire video devoted to different types of antennas, but here we're going to learn about some of the principles of antennas. An antenna is used to either transmit or receive a radio frequency wave. Now, when it's transmitting, it's going to convert electrical energy into a radio frequency wave. When it's receiving, it's going to take this radio frequency wave and convert that into an electrical energy. Also, the shape and size of the antenna is directly related to the frequency at which the radio waves can be transmitted or received by an antenna. Now, when we need to establish a wireless connection between two buildings, we need to have antennas on these buildings with a direct line of sight. Let's bring up another whiteboard and learn about this line of sight concept. Now, in general terms, a line of sight, or LOS as it's abbreviated, is a straight line that can be drawn between two objects. So in this case, our two objects are two buildings with an antenna on top of these two buildings, and we can see directly from one building to another building the antenna, and we're able to draw a straight, unobstructed line between these two antennas. Now, even though the antennas on these two buildings have a direct line of sight with each other, the radio frequency that's transmitted and received between these two antennas typically will not have a direct line of sight, meaning the radio frequencies are subject to refraction, diffraction, reflection, absorption, scattering, etc., as we learned before. And within this line of sight between these two antennas, there's an area called a Fresnel zone. That's spelled F-R-E-S-N-E-L, but it's pronounced Fresnel zone. And within this Fresnel zone there could be obstructions to the radio frequency signals that are transmitted and received between these two antennas. So that's something we have to watch out for, is not only the line of sight between the two antennas, but the Fresnel zone that the radio signals will be transmitted between the two antennas, and to reduce the obstructions within that zone to ensure that there's a clear, strong signal. Now, the Fresnel zone itself defines an area around the line of sight that can introduce radio frequency signal interference if blocked. Now, typically a 20 to even 40% Fresnel zone blockage usually won't cause very much interference with our wireless link. However, you really want to get down to the lower part of that equation. You want to make sure that you don't allow more than 20% blockage within the Fresnel zone to ensure a nice, strong wireless link. So typical sources of blockage within the Fresnel zone, which in this example is illustrated by this oval that I have around the line of sight, are trees, other buildings, and even if you start off with a low percentage of blockage within the Fresnel zone, over time you might find that could increase, simply due to the fact that trees grow. People put new buildings up. So what we can do to alleviate that and to reduce the blockage within the Fresnel zone is simply to increase the height of the antennas, and thereby giving us a new line of sight and a new Fresnel zone. So we've just learned that antennas are used to transmit and to receive radio frequency signals. However, what's used to generate and radiate radio frequency signals is called an intentional radiator. Let's bring up another whiteboard and learn about this. So again, an intentional radiator is a radio frequency device that's designed specifically to generate and radiate radio frequency signals. And an intentional radiator includes the radio frequency device, its connectors and cables, up to but not including the antenna. So everything up to this point
but again, not including the antenna, make up what's referred to as the intentional radiator. However, the actual output of power that is radiated by the antenna element is referred to as the equivalent isotropically radiated power, or EIRP for short. Say that 10 times fast. Now, why this is important is because within the United States, the Federal Communications Commission, or the FCC, governs the usage of radio frequency signals, and depending on the signal that you're using can be either licensed or unlicensed. So, for example, radio stations need a license to broadcast their music and everything else over a specific radio frequency. Well, wireless LANs are unlicensed radio frequencies, and to remain unlicensed, wireless LANs have to ensure that the total output of power, which includes the intentional radiator and the EIRP, is within the FCC rules regarding power output of wireless LANs. And let me bring up a website which shows the maximum amount of power that can be used and still be within FCC regulations for an unlicensed wireless LAN. So you might want to pause the video and jot down this URL for this website. So again, it shows us the FCC rules and regulations for unlicensed wireless LANs. And it's saying in this particular example, for this type of antenna, the maximum amount of power at the antenna, which again is expressed in EIRP, is 4 watts, which we see right here in this very last column. Now, in order to effectively troubleshoot a wireless LAN, you'll need to know some radio frequency mathematics. And in order to understand some of the radio frequency mathematics, you'll need to know about the units of measurements, such as we have right here, that are used in radio frequency mathematics. So let's close out of here and get back to our whiteboard and learn about that. And now let's bring up another whiteboard with the units of measurements that are used within a wireless LAN. Now, our first unit of measurement is a watt, and the basic definition of a watt is that it's a unit of electrical power. And a watt is actually a resulting unit of electrical power. A watt is derived from 1 amp of current at 1 volt. One way to better understand this is by thinking of a garden hose with water flowing through it. The pressure on the water line would represent the voltage in the electrical current, and the water flow that's going through the hose would represent the amps, or the current flowing through the garden hose. So what you can do is think of a watt as the result of a given amount of pressure and a given amount of water in the garden hose. So again, 1 watt is equal to an ampere multiplied times a volt. And one thing to keep in mind is that the FCC only allows for 4 watts of power to be radiated from the antenna in a point-to-multipoint wireless LAN connection when you're using the unlicensed 2.4 gigahertz spread spectrum equipment. Now, 4 watts of power doesn't sound like much, but it's actually enough power to be able to send a radio frequency signal for several miles. So, for example, if you were to have a 7-watt light bulb just illuminating in the middle of the night, somewhere outside, you've got a 7-watt light bulb. On a clear night, that 7-watt light bulb can be seen up to 50 miles away in a 360-degree direction. So, meaning in all directions, you can see a 7-watt light bulb illuminated up to 50 miles away. So it doesn't take a lot of power to be able to send these radio frequency signals from one point to another point. And our next unit of measurement is a milliwatt, and a milliwatt is a 1,000th of a watt. And a milliwatt provides enough power to be able to transmit radio frequency signals over short distances. So, for example, 100 milliwatts provides enough power to be able to transmit radio frequency signals up to a half a mile. And most wireless access points can radiate up to 30 to 100 milliwatts of power. And moving down the line, our next unit of measurement is decibels. Now, you've probably heard about decibels in relationship to acoustics. Maybe when you're purchasing a receiver for your home stereo system, you might have seen a decibel rating for your stereo receiver. As decibels in this type of context is used as a measurement for the intensity of sound, but it's also a unit by which the amplitude
is measured as well. So we learned about amplitude earlier on. So in this context, it's used to measure power gain or loss, as well as the intensity of sound. Now, something to take note of is that power gain and loss are measured in decibels and not in watts, because decibel is a relative measurement. Decibels measure amplitude on a logarithmic scale versus a linear scale. Okay, so what does that mean, laughing boy? Well, on a linear scale such as watts, it's used to measure points of absolute power. An absolute power measurement refers to a measurement of power in relationship to some fixed reference. So, for example, on a linear scale such as watts, it uses a fixed reference of 0. So if you have 0 watts, you have no power. In contrast, in a logarithmic scale, a reference point of 0 can't be used simply because the log of 0 does not exist. So, for example, 5 watts of power is an absolute measurement. In contrast, a relative measurement would be the system is losing half of its power. So again, we use decibels to measure the power gain or loss. And as a wireless network administrator, you need to know the most common amounts in decibels to measure this gain or loss. So let's bring up another whiteboard and learn more about this. So this whiteboard shows the most common amounts in decibels that express a gain or loss in power. So for example, we have -3 decibels, which is half the power in milliwatts. In contrast, +3 decibels doubles the power in milliwatts. And -10 decibels is 1/10 the power in milliwatts, and +10 decibels is 10 times the power in milliwatts. So when you're computing the power gain or loss, -3 decibels will half the watt value. In contrast, +3 decibels will double the watt value. And -10 decibels will decrease the watt value to 1/10 of the value. In contrast, +10 decibels will increase the watt value 10 by 10 times. Now remember earlier I said that decibels are a relative measurement on a logarithmic scale. However, for ease of use, they can be expressed as an absolute measurement. Let me bring up another whiteboard and show you what I mean here. In order to find out how much power a device is consuming at a certain decibel level, we need to convert the decibel level to an absolute value. And the absolute decibel value is expressed as dBm. And this simply means that this is a measured power in decibels relative to 1 milliwatt of power. So a dBm simply equals 1 milliwatt. And going back to our previous example, if we were to add 3 decibels to a watt value, such as 10 milliwatts, that would equate 20 milliwatts. We're doubling this value. In contrast, if we were to add 10 decibels to a watt value, such as 10 milliwatts, that's what it's supposed to be right there, that would provide a 10-fold increase, or 10 milliwatt value. Now, something else to take note of is that these gains and losses, as they're represented in decibels, are cumulative. So, for example, if a wireless access point is connected to a cable that has a loss of -2 decibels, and the cable is connected to a connector that has a loss of 1 decibels, then you're going to have a cumulative total loss of 3 decibels. Also, as I've been mentioning, gains in addition to losses are measured in decibels. However, gains are represented a little differently. Let me bring up another whiteboard and show you what I mean. The gain of an antenna is represented as dBi. So for example, if we were to apply a 10 decibel or a dBi gain to 1 watt, that would provide a 10-fold increase, or 10 watts. So let's take all the knowledge that we've learned here and relate it back to the FCC power guidelines that we took a look at earlier. So we'll bring up that website. So here again, as I stated before, the FCC regulations for point to multipoint specifies that the total amount of power can only be 4 watts, or 36 dBm. And the table below shows us various combinations of power at the antenna, which is the intentional radiator. Again, that's the wireless device, including the cables and connectors, everything up to the antenna. And then the gain of the antenna, and then giving us the total amount of power that is being radiated from the antenna, which is the equivalent isotropically radiated power, or EIRP. So again, to be within FCC guidelines for wireless LAN, the total amount of power at the EIRP, or that's being radiated from the antenna, cannot exceed 4 watts. So for the first example in this table, we see the power at the antenna, or again the intentional radiator, is 36 decibels, which equals 1 watt, and again this is expressed as dBm. And the antenna gain, which is expressed as dBi, is 6, which gives us a total output of 36 decibels, or the equivalent of 4 watts. So when you're creating a wireless LAN, you'll have to ensure that when you purchase the wireless access point, the connectors, the cables, and the antenna, and hook all that stuff together, you have to ensure that the total output, the EIRP, does not exceed 4 watts. And an easy way to do the conversion from decibels to watts is simply to use a decibel to watt calculator. And I've got one such example of that right here, so let me bring up another website. So for example, if I were to type in the value of 36 for 36 decibels, and then to click on this button right here to convert from decibels to watts, click on that and it gives us the value of 3.98, and when we round that value up, it's going to give us a total of 4 watts. So pretty cool stuff there. I recommend pausing the video so you can jot down this URL. Or if this URL ever changes, you can simply do a search in your favorite search engines for decibel to watt conversion calculator, and that should give you several calculators to pick from to do these conversions. And with that, that brings us to the end of this video. Let's go back to our introductory whiteboard and do a recap of what we've learned. So we started off this video by learning that a radio frequency signal can either lose or gain in its amplitude, and that the radio frequency can behave different ways depending on the obstacles or objects that it meets within its path. The radio frequency signal can be reflected, refracted, diffracted, scattered, absorbed. So for example, when a radio wave is refracted, that means that the radio wave is bending as it passes through a medium. In contrast, when it's diffracted, that's what happens to a radio wave as it bends around an object versus through an object. And we also learned about voltage standing wave ratio, or VSRW, which represents a mismatch of impedance in a wireless system. And we also learned about the visual line of sight for wireless antennas, and how obstructions within the Fresnel zone that surrounds wireless antennas can have an impact on the radio frequency signal propagation. We also learned about the intentional radiator and the equivalent isotropically radiated power, or EIRP. And we finished off by learning about the units of mathematics that are used within radio frequency mathematics, such as watt, milliwatt, decibel, dBm, and dBi. And with that, that brings us to the end. I hope that this video has been informative for you, and I'd like to thank you for viewing.